We now have under our belts a picture of the entire universe that is a pretty good one. And it's a pretty impressive fact that we have such a picture. 100 years ago, we knew almost nothing correct about what the universe is like on very large scales, and now we have a picture that fits the data quite well. So the parts of it that we've talked about are basically the fact that when you look into the sky, you see that it's filled with galaxies. So the universe is big. By a galaxy, we mean some collection of stars moving under their mutual gravitational attraction, maybe 100 billion stars per galaxy. There's perhaps 100 billion galaxies spread throughout the observable universe, and they're all moving away from all the other ones. So the universe is getting bigger as a function of time. A crucial fact about this distribution of galaxies through space is that it's more or less uniform. The universe is smooth on very large scales, and this is an incredibly helpful feature as far as cosmologists are concerned, because that means that we can approximate the universe as being absolutely smooth. And that's exactly what we did. We looked at what Einstein said about space and time, and how space and time are joined together in one thing called space-time. That's the theory of special relativity. And that theory of that space-time has a dynamics. Space and time can expand, they can have a geometry, they can change with time, and that's the theory of general relativity. So if you have a universe that is perfectly smooth, that looks the same everywhere, then what you can do is plug that into general relativity and ask, how does a perfectly smooth universe change as a function of time? How does it expand? Where did it come from? Where will it go? We did that, and we derived an equation, the Friedmann equation, which relates the energy density in the universe to the way that space is curved and to the way that space is expanding. In today's lecture, we're going to go a little bit beyond that. We have a picture here from the Sloan Digital Sky Survey of how galaxies are distributed in our local region of the universe. And we said that, look, they look pretty smooth, and that's a very good approximation, and that was very helpful. Today, we will admit and take seriously the fact that they're not completely smooth. There is, in fact, structure there. Some of these galaxies are clumped together in groups of galaxies, in clusters of galaxies, even in things that are larger than clusters of galaxies, walls and sheets and filaments that stretch across the observable universe. At first glance, as cosmologists, we say that's kind of annoying, that the galaxies are not perfectly smooth, because we can really solve a lot of problems in terms of writing down equations and writing down what the solutions are, if everything were perfectly smooth. But on the other hand, it's certainly good news that there are local structures in the universe. It's good that the density is not absolutely constant throughout space. I am much more dense than the air that is around me, and that air is much more dense than the space in between the stars. So there's structure in the universe, and today we're actually going to take advantage of that structure. We're going to use it to weigh the universe, to find out how much stuff there is in the universe, in particular, how much matter there is in the universe. Of course, we've already given away the punchline. What we're going to find is that there's a lot of matter in the universe. There's more matter in the universe than we seem to be able to account for with ordinary matter, with atoms, with hydrogen and helium, and the other elements that we're familiar with from the periodic table. So today we won't get quite that far. What we're going to do is give you evidence that there's a lot of mass in the universe, much more than we see directly, but it will take future lectures to actually show that we're pretty sure that the mass that we don't see is some absolutely new kind of particle. So let's think about the process by which the universe went from being very smooth to having structures in it, to having galaxies and clusters of galaxies. This is an image which is an iconic image in cosmology. This is a picture of the cosmic microwave background. The cosmic microwave background, or the CMB, is the leftover radiation from the Big Bang. When the universe was less than about 400,000 years old, it was opaque. It was hot and dense and giving off light, but the light didn't get that far, it just kept bumping into free electrons. Once the universe was older than 400,000 years, it became transparent, and the light streamed across the universe unimpeded, and that gives us the image we see right here. This is a snapshot of what the universe looked like when it was about 400,000 years after the Big Bang. Now it's about 14 billion years after the Big Bang, so a lot of time has happened, and we can see the effects of that passage of time. In this picture, what is actually shown are the slight differences in temperature from place to place in the cosmic microwave background. The blue spots are a little colder, the yellow and red spots are a little bit hotter, but only very, very slightly. The amount of variation in temperature in the cosmic microwave background is only about 1 part in 100,000. So what that means is that there were slight variations in the density of stuff back at that time. The density of the universe from place to place, 400,000 years after the Big Bang, was nearly perfectly smooth, but not exactly so. You might have had 100,000 particles in this region of space, then 100,001 in this region of space, and 99,999 in that region of space. Tiny variations over an ultimately very smooth distribution. So in lecture 11 in the future, we're going to talk in great detail about what kinds of patterns we see in the cosmic microwave background, how they got there, and what we learned from them. Today, let's just mention that the universe was a lot more smooth back then than it is today. Today, we see galaxies in some places, no galaxies in other places. There's a huge amount of contrast between the density in a galaxy and the density outside. So what happened from the microwave background era to today is gravity. Gravity worked on these tiny perturbations, these tiny ripples in the density of space, to increase their magnitude. Gravity works as a contrast knob. You turn up the contrast in the universe. You take dense regions and they become more dense, underdense regions and they become more underdense. They become less dense. What happens in that region where there's 100,001 particles, the force due to gravity is a little bit more than in that region where there's only 100,000. So this region with one extra particle pulls things toward it. And then it gets two extra particles. And then it has a little bit more mass, so it can pull even more things to it. This is a very slight effect. It takes literally billions of years to happen. But due to this effect, we go from an almost perfectly smooth distribution to a distribution which is still smooth on very large scales, but on small scales you have stars and planets and galaxies. So that happened over the last 14 billion years. Gravity turned up the contrast knob on the universe, and it did so in a hierarchical fashion. What that means is, on smaller scales, things can happen more quickly. It takes less time to build up a density region in some very tiny region of the universe than it does over megaparsecs. Over millions of light years across, it takes at least millions of years. Over billions of light years across, it would take at least billions of years. So the universe forms in a bottom-up way. You first form planet-sized things and star-sized things, then galaxy-sized things, clusters of galaxies, and larger structures. So it's no surprise that we see more structure on small scales than we do on large scales in the universe. We mentioned before that when you actually go and look out into the sky, what you see are a collection of galaxies. So here again is the Hubble Deep Field. This is an image of a randomly selected part of the sky. There's not anything special or especially interesting in that region, but the universe is more or less the same everywhere, so it doesn't matter. You take a picture of a region of the sky, and what you see is it is filled with galaxies. One of the things you notice about these galaxies are that they're very pretty. They are beautiful, they're aesthetically pleasing, and personally I've always wondered why that is the case. I'm not really sure why we find galaxies beautiful. It's hard to imagine some explanation for this from evolutionary psychology. A million years ago, when we were hunters and gatherers, we didn't know what galaxies were looking like. So it's hard to imagine some pressure that we would look at the galaxies sometime in the future and find that they are beautiful, but they certainly are. The other thing is that the galaxies look different. If you look at the different galaxies, some of them are red, some are blue, some of them are smooth, some of them are irregular. Partly this is because we're looking at galaxies at different moments of time. When you look at the sky, because the speed of light is finite, 1 light year per year, you're looking backwards in time. If you see a galaxy that is 1 billion light years away, you're seeing it as it looked 1 billion years ago. So it's not surprising in some sense that the galaxies look different. We're taking snapshots of them at different stages in their evolution. But on the other hand, even today, even the nearby galaxies that are all the same age do look different. Galaxies have a slightly individualistic character. So that's going to be important once we get to talking about what we can learn by studying individual galaxies. So what we're caring about for this course, dark matter and dark energy, is how to weigh the galaxies. How do we know how much stuff there is in a galaxy? Well, the simplest thing to do is just to look and to count. To say, well, if you know there's 100 billion stars, and you know that the average mass of a star is something like the mass of the sun, you're going to guess that there's about 100 billion solar masses worth of stuff in a typical galaxy. But it's always possible, even 100 years ago, people recognized that there was stuff in galaxies that we couldn't see directly. So you want a better way to get a handle on the total mass of the galaxy. How do you do that, of course? The answer is given to you again by gravity. Einstein showed that gravity is universal. Everything that exists in nature, everything that has energy, will give rise to a gravitational field. So even though you don't see it directly, you can tell how much stuff there is in a galaxy by measuring its gravitational field. The more mass that there is in the galaxy, the stronger the gravitational field will be. Now, in fact, we don't really need Einstein to tell us this. Isaac Newton could have told us this. Einstein invented a theory of gravity that is better than Newton's theory of gravity. It can describe things that Newton's theory can't describe. The expansion of the universe is not something that makes sense in Newtonian gravity. For Isaac Newton, space and time were fixed and absolute structures. He couldn't have talked about the Big Bang as some actual expansion of the universe itself. However, Isaac Newton could have talked very easily about a galaxy. A galaxy is in a regime, in a part of the universe, where Newton's theory of gravity is an excellent approximation to what is really going on according to Einstein. So we can think about Newtonian gravity. We can think about the fundamental law of Newtonian gravity, which is the inverse square law. If you have two objects, according to Isaac Newton, they exert a force on each other. That force is proportional to their mass. The heavier they are, the bigger the force is. It's also inversely proportional to their distance apart squared. So as the things get further and further apart, the gravitational force between them gets less and less. What that means is that if one object is orbiting around another one, when the orbiting object goes further and further away, it needs to orbit more and more slowly in order to perform a circle or an ellipse around the thing that it is orbiting. So in the solar system, this is perfectly clear. Mercury is moving around the sun very, very quickly because it's the closest planet. The Earth is moving at some medium speed, and Pluto is moving very, very slowly. It's not just that it takes Pluto longer because it has longer to go. It is actually moving more slowly around the sun because the force due to gravity is much weaker out there where Pluto is. This is, in fact, how we measure the mass of the sun. We don't know. We can't put the sun on a scale and weigh it. What we can do is look at the velocity with which planets are orbiting around the sun and measure its gravitational field. From measuring its gravitational field, we know what the mass is. So let's do the same thing with a galaxy. Let's measure the velocity of things moving around a galaxy. Here's a picture of the Andromeda galaxy. What we would want to do is to look at stuff that is on the outskirts of the galaxy. The difference between a galaxy and the sun is that the galaxy is not all concentrated in one small region. It's clear where the sun is, and outside the sun there's not a lot of mass. But a galaxy is spread out. It's much more diffuse. So you want to look at objects that are as far away as possible because they will be testing the accumulated gravitational field from everything that they are orbiting. If you want to make sure you're getting all the mass, you want to go as far away as possible. And the prediction from Isaac Newton would be that the further you go away, the slower things are revolving around the galaxy. If you measure the speed with which they're rotating, you can figure out the mass. So this project was undertaken in the 1970s by Vera Rubin, who's an astronomer at the Carnegie Institute of Washington. She measured what are called rotation curves of galaxies. So she looked at gas and dust moving around a galaxy, orbiting around it, and in fact, these optical images, these pictures that are taken with visible light, only show you part of the galaxy, the biggest part, the most massive part. But there's also, if you use radio telescopes, stuff that you can see, little wisps of gas and dust far outside. So you can use those as tests for what the gravitational field is. What Rubin found is that even though she looked at gas further and further outside the visible galaxy, the velocity of the orbiting gas did not decrease. As you went further and further out, the stuff keeps orbiting at the same velocity, more or less. The simple interpretation of that is, as you go further and further out, you're feeling the effects of more and more stuff. You have not succeeded in getting outside the entire galaxy. There's still stuff inside. However, we looked at gas that is far outside anything we can visibly observe in the galaxy. So the conclusion from Vera Rubin's observations of the rotation curves of galaxies is that there is stuff creating gravity in galaxies that we don't directly see. Stuff that is distributed in a much bigger, puffier halo, we call it, around the galaxy. So if Rubin is right, and current cosmologists think that she certainly is, the galaxy that we see is a decoration. It's a lit up little thing inside a much bigger structure a halo made of dark matter. So if you plug in the numbers, what you find, according to Rubin's calculations, is that most of the stuff in the galaxy, most of the mass, most of the grams, or most of the ergs, is actually in dark matter. It's not in the visible matter. There's certainly also the possibility that we don't understand gravity, that Isaac Newton's theory does not apply in this regime. That would be a big surprise, and we'll talk about limits on that later. But for right now, the simplest explanation is that there really is dark matter there. But that's a surprising result. That's the first evidence that we have that dark matter is an important part of galactic dynamics. So we would like to check that. Whenever you get a result that is that important, that it says there's a whole new kind of stuff out there in the universe, you don't just accept it and move on. You want to find more evidence that there's something like that going on or that contradicts it. So what you can do is look at clusters of galaxies. So what Rubin did was measure the rotation curves around individual galaxies. Individual galaxies have good features and bad features for this purpose. The good features are that galaxies are very organized. They're very regular. It's clear that there is a disk. It's clear that you're looking at stuff that is outside the visible matter. You can see what you are doing, basically. Clusters are a little bit messier. Clusters are generally not in disks. They're in spherical shapes. They're a little bit disorganized, and you might not be able to measure as cleanly what is going on. You have to be a little bit more clever about the techniques you use to weigh the total amount of stuff in the cluster. Here is a picture of a cluster of galaxies. What you see are, in the picture, at least dozens of different galaxies. In fact, a typical cluster will often have hundreds of galaxies in it. The good part about clusters of galaxies, even though they're a little bit messy, is they have a good chance to be a fair sample of the universe. The worry when you look at an individual galaxy is that individual galaxies are all different. Some galaxies are small and ratty, some are big and very, very smooth. Clusters are all big enough that over the lifetime of the universe, there isn't time for different kinds of stuff to be segregated. Within a cluster, you basically are getting a fair sample of every kind of thing in the universe. The analogy that astronomers sometimes use is you're trying to measure the density of people in the United States in different places. But the data you have are not the total density of people. What you have is the membership directory for the American Astronomical Society. And it's broken down by city. So you can see, for example, there's a giant metropolis called Pasadena, California, and there's a tiny suburb called Los Angeles, California. There's a lot more astronomers in Pasadena, California, because Caltech is there and the Jet Propulsion Laboratory is there, than there is in Los Angeles. But the problem is, the reason you reach this untrue conclusion is because you didn't use a fair sample of the universe. Astronomers do not completely accurately trace the population at large. They are a biased sample. So the good thing about clusters of galaxies is that they are not a biased sample. You get a big enough chunk of the universe that what you see should be representative of what is actually going on. So the next picture that you can see is a computer simulation. It is not a photograph using data. It is the result of a computer trying to figure out how we went from early universe, almost smooth cosmology, to the late universe where you see these structures lighting up. And the good news is the computer simulations do a very good job at matching the data, so we can understand in our computers where different types of matter might be. An interesting thing about these galaxies are they're helping us to answer the question, where is the ordinary matter in galaxies? It might be that there's dark matter, and we're going to say that there is, but even without dark matter, you can still say, just because you see a galaxy and it's lit up, it's shining with stars, that doesn't mean that that's where the ordinary stuff is. What if there's just gas in between the galaxies? How do you know? Again, clusters provide the way to answer that question because they are a fair sample of the universe. What happens in a cluster of galaxies is that the gas in between the galaxies is pulled into the center of the cluster because of the force of gravity. And so even if that gas is dark, even if it is not shining and forming stars, even if in the desolate cold of intergalactic space it would be completely invisible, in the cluster where it clumps together, it heats up. The gas bumps into other gas and it goes to a very, very high temperature. It starts emitting X-rays. Here is an image from the Rosat satellite, a picture of a cluster of galaxies taken in X-rays. And what you see is that it's a much smoother distribution than you would see if you just took a photograph using visible light of this cluster of galaxies. What you see is that in between the galaxies that we thought we were observing, there's a lot of stuff there. What this is the hot X-ray gas in between the galaxies. And you can run the numbers. You can say how many hydrogen atoms, for example, are in the hot gas in between the galaxies versus the hydrogen atoms that are actually in the galaxies shining in the form of stars. The answer is there's more mass in between the galaxies in ordinary matter, just in hydrogen atoms, than there is in the stars in the galaxies themselves. About 2/3 of the total amount of ordinary matter in a cluster of galaxies is in between the galaxies themselves. So because we believe that clusters of galaxies are a fair sample of the universe, what that's telling us is, when we were weighing individual galaxies, we were missing a lot of ordinary matter. Forget about the dark matter. We didn't even get a fair sample of the ordinary matter because most galaxies are not in clusters. Most galaxies are out by themselves, and we can measure the galaxy, but we had no way of knowing what the total amount of invisible hydrogen was. In a cluster of galaxies, we can find it. It's lit up because it is heated up, and it's now emitting X-rays. So, we can find out where the stuff is in a cluster of galaxies. There is a complementary way of doing it. Not only can we look at X-rays that are being emitted by the hot X-ray gas, what we can do is look at the shadow that the cluster of galaxies casts on the cosmic microwave background. The microwave background, remember, is coming from way in the past, from when the universe is only 400,000 years old. If a microwave from the CMB passes through a cluster of galaxies, it will scatter off of that hot gas. So when we look at the cluster, what we see is a dark spot. We don't see the microwave background here because it's been scattered by the hot gas. That is another way, besides using the X-rays, to measure the amount of stuff, and we get a consistent answer. What we find is that 2/3 of the ordinary matter in a cluster of galaxies is not in the galaxies themselves. Okay, so that tells us where the ordinary matter is. But what about this dark matter stuff? Should we weigh the clusters of galaxies and get the same answer? Well, it turns out there are two different ways to weigh the clusters of galaxies. One is to sort of do the analogous thing to what Rubin did with rotation curves. Unfortunately, clusters of galaxies are not aligned in this nice little disk, so you can't get a very simple rotation curve. But what you can do is measure the individual velocity of every single galaxy. There's a theorem in conventional classical Newtonian physics that the average velocity of all the different galaxies moving around is related to the total mass inside. The more mass you have, the faster they will be moving. That is the analogous statement to the fact that the more mass you have in a galaxy, the faster something will be orbiting. So this was first looked at actually in the 1930s, very, very long ago, by Fritz Zwicky, who was a Caltech astronomer at the time. He looked at the Coma cluster of galaxies. He measured their individual velocities, he plugged in the numbers, and he said, look, there's no way to explain these numbers on the basis of the matter we see. There must be matter there that we don't see. He wasn't absolutely taken seriously at the time. It was sort of too early. He was on the spot before people were ready for it. People figured, well, there's just stuff we don't see. There's hydrogen or whatever, ordinary stars and planets that we haven't taken into account. Someday we will find them. Today, of course, we can do better. We can take account of the stars and planets, and we don't find enough. The other thing to do is to look at the temperature profiles of the hot gas to find out what the temperature is of the gas starting from the center of the galaxy and moving our way out. Not only does this tell us how much gas there is, but it tells us the total gravitational field of the cluster of galaxies. And the total gravitational field depends on the total amount of mass. The answer, once again, is completely consistent, namely that even though there's a lot more matter in hot X-ray gas in between the galaxies than in the galaxies themselves, it is still not nearly enough to count for the total amount of matter in the cluster of galaxies. Either by the dynamics of the galaxies zooming around, or by measuring the total amount of gravitational field using the X-ray profile of the cluster, we get the same answer, which is that the total amount of mass is something like 5 times what we actually have in ordinary matter. This seems to be very good evidence that there needs to be something new in there, something that we call dark matter. This kind of argument doesn't completely rule out that it's not some very sneakily hidden form of ordinary matter, but it's pointing in that direction. So, what can we learn from that? Is it possible that we're missing something? Is it possible that there is some dark form of ordinary matter that we haven't seen? It is certainly possible just from what we've said so far. In later lectures, what we're going to do is to put an absolute upper limit on the total amount of ordinary matter in the universe. The way that we're going to do that is to go back to the very early universe, to when it was 1 minute old or a few 100,000 years old, look at the relics that we get from the early universe in the form of helium, lithium, and other light elements, and also in the form of the cosmic background radiation. It turns out that properties of these relics from the early universe depend on the total amount of ordinary matter in the universe in a very specific way. And back then, ordinary matter was not separated into stars, gas, dust, planets. It was all absolutely smoothly distributed. So for once and for all, we can get a measurement of the total amount of ordinary matter. What we find is that it will be very consistent with what we think is there from what we see, from hot gas in clusters of galaxies and elsewhere. In other words, we have more or less a rigorous argument that the matter that we know must be there from the dynamics of clusters of galaxies cannot be ordinary matter hidden in some clever way. It has to be something new. So let me tell you about a way of thinking about what this answer is. I keep talking about the fact that the total amount of dark matter is about 5 times as much as the total amount of ordinary matter. But what units is that in? How should we think about this? Well, remember, the Friedmann equation is the equation we use to govern the expansion of the universe. It relates the total energy density on average in the universe to the expansion rate and to the curvature of space. In other words, if you know the energy density and the expansion rate, the Hubble constant, then you can tell me what the curvature of space is right from the Friedmann equation. In yet other words, there is one particular value of the energy density, which for any given value of the expansion rate will mean that the universe must be flat. In other words, there's a critical value of the energy density that says, if I measure the Hubble constant, and I know that the actual energy density is equal to that critical value, I know that the spatial geometry of the universe must be Euclidean. The spatial geometry must be flat. There must be no curvature. That's not to say that we necessarily have that critical density, but that is a density that we can define using the Friedmann equation. So this is very convenient for astronomers. They will measure the density that we see in units of how much density you would need to make the universe flat, the so-called critical density. It turns out that the ordinary matter that we see in the universe, what we will eventually show is limited very strongly by Big Bang nucleosynthesis and the microwave background, and what right now we're inferring from the matter that we actually see is about 5% of the critical density. Ordinary hydrogen atoms and other forms of stuff in the periodic table makes up about 5% of what you would need to make the universe spatially flat. So the other stuff in the universe, the dark matter that we see evidence for in clusters of galaxies, then makes up about 25% of the critical density. It's about 5 times as much as the ordinary matter. So that's a very interesting result, because 5% plus 25% is 30%. We see in matter, both ordinary and dark, about 30% of what you need to make the universe spatially flat. About 30% of the critical density. The reason why that's an interesting number is 30% is close to 100%, but it's not equal to 100%. So this number could have been anything. It could have been 1/billionth of 1%, or it could have been several trillion percent. It could have been any number, but it's 30%. It's pretty close to being 100%. That makes us suspicious. So 10 or 20 years ago, if you were talking to most cosmologists, they would have said, I bet that we just haven't found all the matter yet. I bet that once we go and do better surveys of the universe, we'll bring that 30% all the way up to 100%. It would be much more aesthetically pleasing if we had exactly the critical density than if we had only 30% of it. In the back of their minds was one other fact, which is that 30% is a number that is not a constant. It changes with time as the universe expands. So the energy density changes in time in a very specific way in a matter-dominated universe, but the critical density also changes, and they change with respect to each other. So if the critical density that we need, if we only have 30% today of the critical density, in the past we had a much closer value to the critical density. Things were very close to being spatially flat. So if we really lived in a universe that had 30% of the critical density and nothing else, we would be right in the middle of a transition regime from a spatially flat universe where the curvature was negligible and you couldn't measure it, to a universe that was highly spatially curved and we had much less than the critical density. The density would be going from almost the critical density and swooping down to almost 0% of it. That's very strange to find us living today in some important part of the universe's history. For a long time, it was thought that this is just evidence that we don't exactly have a good measure of the total amount of matter in the universe. Less than 10 years ago, of course, in 1998, the true answer was revealed. The answer is there is stuff out there that is not matter. It's dark energy. And that dark energy, in fact, makes up almost precisely the 70% that we need to make the universe spatially flat. We do have the critical density in the universe, but most of it is not matter. Most of it is something even more mysterious.